is also a random variable. But the question then of interest is, if x1 has this distribution and x2 has that distribution, and then what is the y's distribution? What's the distribution of y? So if I randomly take a sample from Rhode Island and a sample from California, okay? And then what is this quantity's distribution? Okay, so the argument is going to be that this guy is going to be some kind of convoluted function of these two distributions. Okay. So that's your intuition, and then your intuition is correct. Okay, so the distribution, okay, the distribution of y is going to be some convoluted function of the two. Okay, so because what happens is when you every time because y is x1 plus x2. Okay, so if I take a sample of x1 from Rhode Island, then the Californians would be y minus x1. Okay, so which means that every time when I, okay, so actually the sample I gave here is the opposite. So what I have is I take a sample from California, and then I ask what is the weight of Rhode Islanders, and given the value of y. Okay, so the what's so the probability that, so remember the distribution basically gives you a probability distribution. Okay, so if I ask what is the probability of x2, okay, and then what's the probability I draw a value of x2 from the California, okay, and then I want to know what's the population of total weight at y. That means that would depend on the probability I draw a sample of y minus x2 from Rhode Island. Okay, so this, if you have found that this is a little twisted, let me give you an example. Okay, so let's say you throw two dice. Okay, dice 1 has 6 sides, right? 1, 2, 3, 4, 5, 6, and dice 2 has 1, 2, 3, 4, 5, 6. Okay, so then if I ask you what's the probability you get a dice 1, you get at 1, and a dice 2 at a 3, then I'm asking you what's the distribution, what's the probability of getting the dice at y that's equal to 4. Okay, so then you know that the probability of getting 1 in the first dice is 1 over 6, and then the second one is well, 3 is also 1 over 6. So the fact that if you throw two dice, the probability of getting one is 1, the other one 3, is 1 over 6 times 1 over 6. Okay. Okay. So now, but if I ask you the y value is 4, then in addition to 1 and 3 combination, you can also have 3 and a 1 combination, and a 2 and a 2 combination. So which means you need to add up all of this. Okay, so this is why this is an integral, means it's a sum of all these possibilities. Okay, so that's the idea that a convoluted, the probability distribution of a sum of two random variables is the integral of the convolution of the two distributions. Okay, so if you have trouble appreciate this is a crucial step that you needed to wrap your head around. Okay, so this is a very important step. You needed to digest. You need to accept. If you have trouble, then I ask you to place dice. Okay, the 2 dice. So for example, you can ask, you throw 2 dice. Okay. So they say there's a side of 6. You can ask, what's the probability get both sides to be 6? In other words, if your y is 12, then the only choice you have is 6 plus 6. Okay. So then you can ask, what's the probability you're getting that? That probability is definitely just 1/6 times 1/6. Okay. So that means you only have 1/36 chance of getting a combined value of 12. However, if you combined value is 4, then that has more options, right? So we just said that you can be 1 plus 3, okay, it can be 3 plus 1, okay, and it can be 2 plus 2, okay. So you know that each is 1/36. So this guy is obviously is 1/36 times 3, okay. So immediately you see that the probability of getting a sum y value to be 4 for 2 dices is higher comparing to the y value of 12, okay. And the same is true for for 2, right? So if y is equal to 2, then because the minimum value is 1 for each, so then it's going to be 1 plus 1. You don't have a choice. So in that case, it's going to be 1/36. Okay. So this kind of a game that you should actually play a little bit to accept this. Okay. So so after we get over this hurdle, then the rest is algebra. So if you accept this definition, then the rest of the algebra. Okay, you see? So we can rewrite Px1, the distribution of Px2, in terms of a Fourier transforms. Okay, so we'll Fourier transform into some conjugate variable. So if this is a position, then this would be something like a wavelength. If x1 is time, and this would be frequency. And if this is weight, well, this will be 1/weight. What is 1/weight? Well, you can think of means what it means is the conjugate variable of weight. In any case, you can define this some Fourier transform. Okay, so this is a general definition of Fourier transform, and then the reverse of that from the Fourier transform, there's a difference of 2 pi here. Okay, so if you define this as 1/√2 pi, this is 1/√2 pi. Okay, but in any case, if I define it this way, as long as you define this self-consistently, you are fine. Okay. Okay, so now having defined the Fourier transform and reverse Fourier transform, then I can ask what is the Fourier transform of y into the conjugate space. Okay, so then this is the reverse transform of y. Okay, so now let's see how this, I call them characteristic functions. Okay, it's just Fourier transforms. Okay, so let's see how they are related. Okay, so the rest is just simple algebra. So this Fourier transform of y is defined as such. And then because I know what the y is, okay, it's just this guy here. So this guy is simply this. If you are not sure, you can rewind this video and then go back and check. That's exactly what we had. Okay. Okay. So now the next then is just algebra. Okay. So I can put so I can rewrite. I can add a term here. I can add a term here, and by taking it away at the same time. Okay. But I know y minus x2 is just x1, and then so dy is a dx1. So then I can rewrite this integral as two separate integrals. Okay, so you might say, wait a second, what did we actually do? So what we just did is make that convoluted integral in the py into the conjugated space, the conjugated variable t space, in such a way that it's a simple product. So convoluted integrals will always look scary, right? And then now it's just simple, their Fourier transforms are just simple product. Okay, this is actually very useful. Okay. Okay, so namely, what we have arrived at is a major deal. Okay, that is x1 is a random variable. In this case, I said it's from Rhode Island. And x2 is some guy my age from California. And the y is average between Rhode Island, is the sum of two random variables from Rhode Island and California. And that this distribution in the reciprocal space, the probability distribution of this quantity and the probability of this guy and this guy, they are simple product in the reciprocal space. Even though in real space, in real unit of weight, and there are convoluted functions, and but in the reciprocal space, okay, they are simple product. So this is a very, very powerful statement. It's independent of what the underlying physical quantities. This can be positions, and it can be wildfires, can be temperature, can be a Brownian particle in California, Brownian particle in Rhode Island, or air pressure, temperature fluctuations of the seasonal change, whatever. Okay, so so the beauty is that this becomes a simple product. Okay. Okay, so if you accept that, okay, so now we can make a connection with what we previously had. So what it means is we had a 10, right, random variables identically distributed. Okay, so then this yn would be the reciprocal, the distribution function in the reciprocal space. It would be a simple product of the n, but because they're identically distributed, then this just becomes the nth power of that. Okay, so this is a major milestone in our algebra exercise so far. Okay, so if you are not clear how we get it to this point, you should rewind and watch over again. If there's a question, you should ask me, and then we can set up a separate individual Zoom meeting to clarify any of these issues. But if you don't have an issue, if you accept this, then we can move on. Okay, so So we said we go back to yn distribution. This yn is just this. So what it means is then we can have this T would be the reciprocal space quantity of this guy here, okay? So if this is position, in a unit of position, this would be in a unit of wave vector. And if this is frequency, this would be time. If this is time, this would be frequency, and so forth. Okay, so from here to here, we didn't do anything, we just copied, okay? Now, if you accept this, get to this point, okay, then we write out what this guy is, okay? This guy. So we write out this piece here, okay? So we write it clearly out what this is. Remember, this x1 is just this x1 minus mu, okay? So this is just definition. So this is the definition of the Fourier transform. So there's nothing to argue because this is our definition. Okay, so if you accept that, then what the next one is, I take a Taylor expansion of this exponential term into this forms. Okay, so 1 plus blah, 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 okay. And then what I find is the first term is just an integral of this probability. But because we already normalized everything, the probability is gonna, the integral of the probability is giving me 1. The second one is because the probability this is an even function, okay? And then when we do this integral here, and this will give me a 0, okay? And because remember this guy here is defined around the mean, okay? So then because x1 is the deviation from the true mean, if you integrate over all possibilities of the whole population, then this gives me 0, as it should. Okay, the second term here is a square term. This will not be 0, okay? What is that? And then this one, if you go back and check the definition of sigma square, remember this is the true population mean square displacement. So this is just that, okay? If you put this back here, you get this 2 sigma squares cancel, and then you get a 1 minus t squared over 2n. So this guy, this is the reciprocal space distribution for x1 is 1 minus t squared over 2n. Okay, so then this yn distribution is just the nth power, right? So because this comes from the fact that they are identically distributed because it's drawn from the same distribution, okay? So this is just the n terms multiplied together, so you get an nth power. But this guy here is nothing but the limiting form for exponential, okay? So this is only true when n goes to infinity. Okay, so now you're gonna say, hey, Professor Lin, you cheated. You told us that this is a good deal because you don't have to take a whole measurement of the sample. It's true, okay? But it turns out this n doesn't have to be infinity, and something like a 10, this converge is pretty good, okay? So strictly speaking, this has to be infinity, but practically speaking, you do not need it to be n to be a billion to have this two to be in agreement. And in fact, when n's on the order of 10, this is already in agreement. Okay? If you don't believe me, you can go and use Mathematica, the write code, and do some calculation, and then to show that this is indeed true. Okay. Okay, so we have this, and then we put it back. Okay, so this is the, remember, this is the reciprocal space, right? So we needed to convert back to the real space. And then, so we need to do a Fourier transform back to the real space. So now this is just algebra. And then you put it back here, and then you have this. And then this is just a Gaussian integral. If you don't know how to do the Gaussian integral, you can go check out the Wikipedia. But I trust you know how to do, since you guys are graduate student and you got into Brown, so you should know how to do this Gaussian integral. Okay, so once you finish this, you get this piece here. Okay, so this is what we're aiming for. So what we're saying is that the random, we take a sample, small sample of n. This is the sample mean. The probability of getting this value satisfy this distribution. Okay, so you see what this guy is the probability of this guy satisfy this Gaussian distribution with a Gaussian width that depends on the number of time you take, the sample size you take. So if you, so obviously if your population distribution is wide, and this is going to be wide, but you can get a pretty good measurement of mu by taking, say, if you take a sample of 10, this would be something like a 3 something, right? And then, so if your population mean whatever it is, you will get, let's say, your variance of a Rhode Island, say, the mean value of 175 pounds with variance of 10 pounds, then you can get a pretty good measurement of, get a good guess of this mu value to an amount by the amount of the square root of that variance, okay? So if the variance is 10, and then this is 175, this is 10, you get something like a 10 divided by 3, still 3 point something, right? So you get something like a 172 to 178-ish, okay? And then you will get a normal distribution, and you can get a very good guess of this mu value, okay? And then, and final point is that if you take this n to be really large, then you get the you get a really good measurement of the true value of mu. Of course, strictly speaking, you get a true value of mu is taking measurement of the whole population. Okay. And then, but in the case of if you have not a 50,000 sample, but a 5 billion sample, then this is the only thing you will have. Okay, so central limit theorem will be your only option. Okay. Okay, so finally, okay, finally is that, why am I not able to? Oh, this is the bottom of the page. Okay, so so if you take n times from a random sample, okay, you will get n times of the mean value plus minus square root of n times the population average. Okay, so in other words, you will get So if you take n times and then you average, what you get is going to be n mu plus minus square root of n sigma divided by n. So what you have is you're going to get to be very close to the true mean plus minus sigma of a square root of n. Okay, so this is the key. This is what we do in, this is the formula we give to the student, that this is the mean value, this is your, what we call the standard error, okay? So this is the note I gave, I posted it on the page, okay? In all the Canvas page for physics 30, 40, and 50, okay? So that's all. I'm going to end here. I am going to stop sharing and I'm going to stop recording. I'm going to pass the information to you guys. And if you have questions, and please email me. We can set up a individual Zoom time to go over the notes, okay? Stay safe. Bye.